We're going to be chatting about a fairly recent paper by Google Research called Self-Discovery, um, with a subtitle of Empowering Language Models with Autonomous Reasoning Structures. So the idea of this paper, before we delve into it, is to be able to find some low-cost methods in order to be able to improve a lot of the reasoning performance of large language models. And furthermore, to even be able to address this problem of how do you improve the reasoning of large language models. And for this, I want to get started by first going through the main background of this paper, or the main crux of this paper, which is to give a little bit of an overview of prompt engineering. Now, prompt engineering has a little bit of a mixed reputation in the AI community. And a lot of this mixed reputation comes from not fully understanding what the role of prompt engineering is. When it was first introduced, there were definitely two de facto camps: those who believed very strongly in prompt engineering, and those who viewed it as something that was magical, that is going to disappear at some point once language models become more powerful and more effective. I am of the camp that it certainly is not going to disappear, and that it certainly is something that requires a lot of very careful study and very careful implementation, even if you are using very, very powerful and very large language models. And we can go through many of the reasons why, and this paper absolutely highlights the need for prompt engineering. So what are some of the, settings for prompt engineering, why we should consider it? One is a practical reason. It is a very resource-effective way how to get the best performance out of these large language models, and it can provide some stellar results without using fine-tuning or RAG or anything that's very expensive. Moreover, for many types of tasks, I will even argue that prompt engineering is absolutely necessary, even if you're using a very large language model, even if you're fine-tuning, and even if you're using RAG, you still will need to do some prompt engineering. There is a mathematical reason for it as well. The way that these models operate is by next token prediction. And so prompt engineering allows you to understand a little bit more what's going on under the hood by probing into what I call the probability landscape of the model. The last is more philosophical, but the philosophical intuition also guides a lot of our intuition, like a lot of our technical intuition, which is that these models learn a representation of language at the end of the day. I'm not of the camp that goes as far as to say that it learns a world representation, but it does learn a representation of language. And so when you provide for it kind of a miniature model of what representation it has learned in order to be able to get the best results. And that allows us to understand a little bit more how, well, first of all, like we as humans have put together language, because it is mostly human data that these models are trained on. And secondly, a little bit more what this whole idea of next token prediction would mean. So some prompting techniques that people have used so far are, well, the most basic one is direct prompting. This is, of course, the technique that we want to, in the end, move towards. Just to do direct prompting, where the user input is the exact same thing as what ends up being engineered. As I said before, and as we're going to see further in this paper, it's not possible to achieve this at this point, even with the largest and most effective language models. So again, for direct prompting, especially when you have something that's a more complex problem, such as a math problem, such as I went to the market and bought 10 apples, I gave 2 apples to the neighbor and 2 to the repairman. I then bought 5 more apples and ate 1. How many apples did I remain with? Direct prompting would just restate the question exactly as it is as an input to the model. Chain of thought prompting adds an additional layer to it. And there's multiple things that people have called chain of thought prompting inside of the literature. You would still use the question itself, but the main part of chain of thought prompting is that you add an additional step to it called a meta prompt. And in this case, at least in the original paper about chain of thought prompting, the meta prompt was, let's think step by step. Now, when you're talking about zero-shot chain of thought prompting, This is the entirety of chain of thought prompting. You can enhance this further, which a lot of people refer to as chain of thought prompting, when it's combined with a few shot examples, where in addition to this problem, you have also other problems that you present to the model together with elaborate reasoning solutions. In this talk, we're going to be focusing on the meta prompt aspect of prompts, and we're going to be focusing on zero-shot prompting. So for us over here, chain of thought prompting is going to refer to the prompt together with the chain of thought meta prompt, which is let's think step by step. There are more elaborate ways how to develop these meta prompts, such as plan and solve prompting, where the meta prompt becomes a little bit longer and a little bit more human. Not just let's think step by step, but it's more how humans would kind of in a meta sense solve problems. You tell a human to try to understand the problem first, and then to devise a plan to solve the problem, and then to carry out the plan and solve the problem step by step. Now, of course, when you're working with your colleagues, you usually do not go into that much meta prompting, but if you're working with an intern or with a student, then you do give these types of meta prompts to humans as far as like what it is that they're supposed to be doing to carry out these steps. Now, turns out that some of these types of additional layers of meta promptings for what are the actions that humans need to take does work better and does often work better than chain of thought prompting. So plan and solve prompting is one of these examples. And very similarly, there's a few shot version of this where you have a plan and solve template for your few shot examples. But again, we're focusing on zero shot prompting over here and on creating the appropriate meta prompts. There are some other advanced prompting techniques in order to be able to get better responses. One is self-consistency, which I guess it's not so much the way that you construct your prompts, but how you do inference. So you can combine self-consistency with any of the prompting techniques that you have. The idea is that you prompt the model multiple times, and then you find either the majority or the plurality of the responses that are the desired responses that you want. The tricky thing with implementing self-consistency is kind of twofold. One is that it's very, very costly because you are going to be doing inference something like 10 or 15 times. This was another paper by Google Research that found that self-consistency drastically improves performance in tasks such as mathematics. The second thing is that you need your responses to be comparable. You need to be able to extract from it a verifiable truth in order to be able to do a majority scoring at the end of the day. So another another technique that has occurred in literature is OPRO. So this is using an LLM as an optimizer itself to improve its own meta prompts. So the idea over here is that you pair your prompts together with tasks. You feed it into an LLM, you provide it scores, you ask the LLM to rescore it, and then to modify, to give a better meta prompt that it would think would give a better score than the existing scores. And it's an iterative loop, so it is also expensive. And this allowed the researchers to come up with the meta prompt of take a deep breath and work on solving this problem step by step, which improved chain of thought prompting. And then in the developer community, after this paper came out, people talked about using emotional intelligence, using please, using flattery for language models, and that became kind of an established meta prompting technique. Or even further than that, something that in the developer community people have discovered was for math problems in particular, that the best meta prompt that you can actually give it is pretend that you are Captain Kirk on the Enterprise and that you are about to go into this mission that you're going to fail. Solve the math problem accurately, as accurately and precisely as possible. And that drastically improves the performance. And so there's many things that people have found from LLMs optimizing and then using human intuition on top of it as well. So OPRO actually spurred a lot of things in the developer community with just this one response that it gave out. And lastly, majority voting, very similar to self-consistency, but this time you can modify various aspects of your prompt and make some decisions of which of your outputs are better. I noticed there are a few questions inside of the chat. I'm going to address those closer to the end of the talk. All right, so what are some of the challenges in prompt engineering? So one of the biggest challenges that there is in prompt engineering is that there is no one size fits all for user queries. And this becomes particularly challenging if you're working on building LLMs in an enterprise setting. Every task has its own unique intrinsic structure, and different types of prompt techniques are going to just work better. For example, if you're using few-shot prompting, then least to most prompting is more effective than a COT prompting whenever you have symbolic manipulation or compositional generalization. And there's many other examples of this as well. The meta prompts themselves also need to be very closely adapted to the user query. Saying let's think step by step is very good for a math problem, but it's not going to be very good for something like, I don't know how to install this on my computer. Where am I supposed to navigate the documentation to be able to figure this out? That's as much as you can think step by step, it's more of a searching problem and understanding how to utilize and associate multiple things, not in a linear fashion with respect to each other. Another problem that arises with prompt engineering is that human interpretability and machine interpretability do not directly align. So this is where the philosophical question becomes the philosophical nature of prompt engineering becomes very important to understand what is the nature of the language that the model learns. Ideally, we would really want to have a perfect alignment, and we would ideally really like to be able to use human intuition of how we would construct meta prompts and construct instructions in order to be able to effectively prompt the model. But as we have learned, even in practice, that's not the case. Saying that you're Captain Kirk to the language model makes it perform better in math, as opposed to saying that it's very, as humans, maybe saying that you're, a rock star math professor, maybe that would be a better thing, but actually it's Captain Kirk, not a rock star math professor that makes it perform the best. And lastly, the last problem is that the way that a lot of prompt engineering works today is that you consider the entire engineered prompt as its own atomic unit. So when people do prompt engineering under the hood, most of the times they take a user query and they put it into a much larger template, together with a meta prompt, together with few-shot examples, together with maybe some context. But it doesn't break down different parts of a prompt or identify different parts of a user query or different features that are inside of a user's intent to be able to appropriately pair it with different types of meta prompts that might be the most helpful to be able to answer that question. So kind of to answer all three at once, Google researchers came up with a method called self-discovery. So their idea is to try to self-discover reasoning structures within user queries, within these questions, in order to provide better meta prompts. And so the LLM itself would be self-discovering the reasoning structures the meta prompts that would be needed in order to be able to construct the most effective prompting for these questions. So on a high level, the flow is broken down into two stages. The first stage is the discovery stage, and the second stage is the inference stage. In the discovery stage, what they do is they take a language model and a task, and they take various smaller atomic reasoning modules, and they combine this in order to discover which of these smaller reasoning modules are going to be the most effective to the task at hand, and further adapt the reasoning modules so that they are directly addressing the task at hand. Then, using this in the class of tasks that the original task was in, they're able to do inference on those classes of tasks that the original task on which they adapted the meta prompts to in order to be able to provide better answers. So this is on a very high level. And let's go into a lot more detail into this. And we'll go through this actually maybe at least 3 times. Stage 1 is the key stage that makes this technique work. So stage 1, they break it down into 3 different actions: select, adapt, and implement. In the select stage, what the language model does is it takes from a set of seed modules, so a set of meta prompts or a set of reasoning structures, and it's paired with a task, and you prompt the language model that given these reasoning structures, they use 39 reasoning structures. So given these 39 reasoning structures and given this task, which of the 39 are going to be the best suited to be able to solve this task? And you get some selected modules from that. They do not specify that they say how many they select, but let's just say they select like 5 or 10 of them. Then in the next stage, they take the selected modules, they pair it again together with the task, and they prompt the model, given these selected modules, for the purposes of this, we assume 5 or 10, we're going, you ask the language model to take each of these, and given the task, can you adapt it to make these more specific to the task so that it solves the task in a better way? And lastly, you have the implementation question, which is now we have these adapted questions, now we have these adapted meta prompts, and we have this task. Can you put this in the appropriate format in such a way that we can use this later to be able to prompt another language model in order to be able to provide these results? And so the key thing over here is that the established format that you really want to get it into is going to be a JSON template under here in the blue square of the reasoning structure, where when you prompt the model later, you're going to be asking the model to be filling out this JSON template. So for example, if your question had some categorization about type and color of items, and then when you're going to be prompting the model later on to answer a question, it's going to fill out this template and it's going to be answering the question of what is the type and color of each item. So symbolically, just same thing, the steps: select, adapt, and implement. Your inputs to the model are going to be the reasoning modules together with some task examples, together with the meta prompt to be able to get your selected reasoning structures. Then the next step is you have your adapted meta prompt, you have your selected modules and your task at hand to be able to get the adapted reasoning structures. And lastly, you have your adapted reasoning structures with your task, with a meta prompt, together with a human reasoning template. So this is a format, this is just the part that tells the LLM that you want your response to be inside of a JSON format in order to be able to get your final implementation module. And so just to be very, very clear and very precise on this step, you have 3 steps of inference, which is non-trivial, but it still is very minimal to be able to get good reasoning pathways in just 3 steps. Here are some examples of the meta prompts, or well, the complete prompts for each of the actions. So for select, of course, the meta prompt would be select several reasoning modules that are crucial to utilize in order to solve the given task, and then kind of reprompting it again at the end, select several modules that are crucial for solving the tasks above, just to verify very, very critically that this is what the machine has to do, and together with what the reasoning modules are and the task examples without an answer. Adaptation, similarly, you sandwich it between 2 meta prompts, rephrase and specify each reasoning module so that it better helps solving the task, and then adapt each reasoning module to better solve the tasks. And finally, implementation, which is paired with, of course, the human template, the human JSON template. And once again, with a meta prompt, operationalize the reasoning modules into step-by-step reasoning plan in JSON format, and then implement a reasoning structure for solvers to follow step-by-step and arrive at correct answers. Some examples of the reasoning modules that they use. So they used a total of 39. The paper lists all 39. Here are some examples of them. Some of them are questions, some of them are more meta-prompt style. So questions could be like, how could I devise an experiment to help solve that problem? How can I measure progress on this problem? Or more of a meta-prompting style would be critical thinking. This style involves analyzing the problem from different perspectives, questioning assumptions, and evaluating the evidence or information available. It focuses on logical reasoning, evidence-based decision-making, and identifying potential biases or flaws in thinking. And so depending on the task, different versions of these meta prompts, different sets of these meta prompts are more or less effective. And the goal is to be able to select those which are going to be the most effective. There's one over here, emphasize teamwork, open communication, and leveraging the diverse perspectives and expertise of a group to come up with effective solutions. That one's kind of funny because it's very, very human. And you're not using an ensemble technique over here. So you're not actually using anything about LLMs working with each other. So that one's interesting because it's a linguistic technique over there at the end of the day, but it's a very human prompt over there. So the self-discover prompt, the output, we'll see some better examples later on, but it breaks down the task into subtasks. So you do have it in JSON formats that are very specific and really reflect the nature of the task. So identify the chain of events of the story, identify the consequences of each event. So it has very precise words that it discovers. Right, and then it devises an algorithm for how you solve the problem. So you end up getting this template, you fill in the template with the assumption that by the time you get to the end of the template, it's going to be able to solve the problem completely. All right, the stage 2 is very simple. This is the inference stage. Compared to stage 1, you only prompt this once. So to make the most effective use of this technique, you divide tasks up by task type. And so after stage 1, you have one of these templates as before. And so, so that template would be this DI. You look at tasks inside of that task type capital T, and then you put in a meta prompt, this reasoning template, and the task for each task in that task type, and you ask it to solve it. And the meta prompt that you put is you follow the step-by-step reasoning plan in the JSON to correctly solve the task, fill in the values following the keys by reasoning specifically about the given task. Do not simply rephrase the keys. And so in this, what it does is it fills out this template for each of these meta prompts, which are now explicitly tailored to the task or the task type, in order to be able to solve the task. All right, so how does this technique fare compared to other techniques? It's quite elaborate, it's quite specific as well, while it's not terribly expensive, it does require three inference steps on stage 1, and if you want to make it tailored to question like task specific, not task type specific, then of course that would involve 4 inference calls for each task, which is already getting to be quite expensive. So why bother with this? What does why bother with this? So the researchers tested this in very hard using very hard data sets in their experiments. They used Big Bench Hard, which is 23 very challenging tasks, which involves algorithmic and arithmetic reasoning, natural language understanding, use of world knowledge, multilingual knowledge and reasoning. They also used thinking for doing and math as their data sets. So they really wanted to focus on very complex questions, first of all, which is where these large language models fail, and fail especially with direct prompting. The way that they evaluated performance is by accuracy and exact matching, and they actually did a lot of manual extraction. It's very important to point this out, how thorough this was and how human involved it was. because of course, these are very, very complex problems, very, very complex questions. And so it's not as simple, while some of these are multiple choice, it's not as simple as, it's not as simple sometimes as saying, the model said that the answer choice was A, B, C, or D. And even if sometimes these models do output that the answer choice that is correct is A, B, C, or D, there's sometimes a lot of additional things that the model also outputs around that as well. And so it's a very, very involved, their evaluation was very, very involved. Example tasks, just to see what they tested it on. So from BBH, Big Bench Hard, one such example is tracking position. So Alice, Bob, and Claire are playing a game. At the start of the game, they're each holding a ball. Alice has a yellow ball, Bob has a blue ball, Claire has a pink ball. As the game progresses, pairs of players trade balls. First, Claire and Alice swap balls, then Alice and Bob swap balls. Finally, Claire and Bob swap balls. At the end of the game, Bob has the, and then you have to answer that. And so, of course, like for us as humans, when we look at this, like we really do have a world model in our mind. We probably are visualizing this. Maybe, you know, one of those games about like, you know, putting like the cups under, like putting like the balls under like the cups and then swapping like the cups. Maybe that like evokes like something in our minds, but we really visualize this to be able to solve this. And so it's very interesting to be able to break this down step by step to make this a purely linguistic problem to be able to solve this. Theory of mind, on the other hand, Chloe loves the undershirt. Avery entered the dining room. Aiden entered the dining room. The stockings is, that seems like a grammatical error. The stockings are in the crate. Avery exited the dining room. The grammatical error was not mine. I copied and pasted this directly from the data set. Aiden moved the stockings to the cupboard. Aiden exited the dining room. Avery entered the sunroom. Aiden and Avery plan to use the stockings soon. Based on the above information, who among the individuals would most benefit from receiving helpful information? Like this almost feels like with like that last question, like one of these like super trick problems where you set up like something that's like a positional problem, and then you ask something that's completely different. So these are very, very difficult problems. It is a problem that is possible to solve. Basically, if Aiden and Avery plan to use the stockings soon, then you have to figure out who does not have enough information about whatever the setting is. So there's a lot of meta extraction that you have to do from these step by step, from the steps which are given in this problem. All right. And and not like there's a lot of meta extraction, and you have to understand what information each person knows also, which is a very complex problem. And so, of course, we have theory of mind. Models do not have theory of mind. And so how do we model something like a theory of mind using only meta prompting? So the models and the baselines that they tested against. So the models that they tested were GPT-4, GPT 3.5 Turbo. They looked at an instruction-tuned PALM 2L, and they looked at Llama 2 70B. And the baselines that they tested their techniques against were, of course, the prompting techniques that we chatted about, direct prompting, COT, and plan and solve. They also looked at COT self-consistency, where they used 10 iterations for it. So self-consistency, again, it's a technique where you prompt the same thing multiple times. In this case, they prompted it to 10 times to get the answer. And then they use some type of a majority or plurality scoring. They voted by plurality in this case. Then they did also a type of a majority voting for each reasoning module. So what they did was they prompted modules to solve the task by appending each of the 39 reasoning modules to the task. And then they used majority voting to take, so they prompted them, so they had the task at hand. They attached to it each of these reasoning modules individually. Then, based on the 39 outputs that they got, they used the majority voting to be able to say that, okay, the majority, let's say it's a multiple choice. Let's just say the majority of these 39 answered A. Then you would take all of those reasoning modules which answered A, and then you would construct a new prompt, a 40th prompt, which has all of those that answered A, and you just attach the reasoning modules that answered A. So you do not adapt the reasoning modules. You just kind of look at which are the best reasoning models in the sense of a majority voting. And then they did a gold standard best of each RM. So they actually did like human responses, where they took each of the reasoning modules, they took the answers, and then they took whichever ones got it correct, they attached those reasoning modules as a gold standard baseline as well. All right. So the results. Unfortunately, the results are actually kind of sparse. I wish they reported more about it. The main results, they only reported about Palm 2 and GPT-4. So as far as just baseline accuracy on each of these, when they looked at baseline accuracy with each of these models, with these different types of meta prompting structures, they found that actually it seems like the greatest improvement happens with GPT-4 together with the self-discovery structure. And you do see some very drastic improvements over there. Palm 2 showed very modest improvements, very good improvements as well, actually, especially for T4D when you look at it. And the self-discovery structure consistently outperformed just simple COT or the plan and solve method. Some of the more in-depth responses, some of the more in-depth results that they looked at were they tried to look at what are the best types of problems for self-discover. Does this, because again, there's no one size fits all that for any type of a prompting technique, are there some tasks that are better suited for self-discover than other tasks? So self-discover did show improvements in all categories, but it showed the greatest. So basically anything that's a positive bar over here is an improvement over a baseline direct prompting or a baseline over COT using self-discover. But it showed consistently the most improvements whenever there were questions that required use of world knowledge. It's kind of interesting to me that for multilingual, it seems that direct prompting, it seems like the only way that they could achieve this is that direct prompting actually worked better than COT prompting, which is interesting to think about. But then also thinking maybe about the task at hand, COT prompting asks you to think about things step by step, and multilingual questions might just not be suited for step by step, and it might be misleading. So how efficient is self-discover? So self-discover, again, it uses 4 inference steps per task type. Well, it uses 3 inference tasks per task type and then 1 inference step for actually querying the task. And so if you look at some of these different tasks, some of these different prompting techniques, well, the worst is, of course, going to be something where you're going to be trying to query the language model multiple times, as many as 40 times, such as for majority voting for each RM or the best of each RM. Right, and then like COT and self-consistency is very high as well. So the point over here is that whenever you're actually working on building out these language models, you want to be as close to the left in this graph as possible because you don't want to use up a lot of inference time. With infinite time, of course, we can get more and more accurate answers, but we don't want to use up a lot of inference time. And we want to get as high as possible on the accuracy. And so self-discover scores extremely well because it is the highest in their accuracy. It's not the lowest in their inference time because it does require 4 prompts. But it's interesting to compare this with also the majority voting for each RM, where the LLM just looked at every single reasoning module and just ended in majority voting, that the accuracy is actually kind of low for that. For COT and self-consistency, even that is higher. And that even for the best of each RM, the human gold standard, where these reasoning modules, these meta prompts, which are going to be attached to this prompt, provide the correct answer. each individually. Self-discovery with adapting each of the prompts does perform slightly better than just humans choosing the best of the reasoning modules. And it's much less expensive. So how does self-discover compare to baselines? So generally it performed better with higher accuracy responses. And you can also see some of these responses are more elaborate and more human readable. So here is the prompt. This SVG path element draws and you have to answer it as a heptagon. And you can read each of these responses, and it's only in the self-discovery reasoning structure that it actually uses some of the inputs directly, actually extracts some of the content that was inside of the question directly, and then puts it into its algorithm to be able to solve the problem. And so it's very, very human interpretable also at the end of the day. There's a couple of ablation studies as well, where you can ask, is every action of self-discover needed to be able to get these responses? So remember the actions were select, adapt, and implement. And so if you just select the so hold on. I apologize. There's someone mowing the lawn outside. Do you guys hear that?
A little bit, but it's not super loud in the background.
Okay. It's very loud for me. Usually these things get filtered pretty well. I just wanted to check and make sure that. Okay, cool. All right. So ablation studies. So the actions that you had were select, adapt, and implement. So how well do these does performance work if you only use a select, if you only use a select and adapt, or if you use all three? And you do see improvements over COT with any of these steps. So even if you want to, if you want to implement a more cost-effective version of self-discovery, so that you do not use all three steps, so that you do not have 4 inference steps, but maybe you have only 2 or 3, and then you can still see improvements over COT just using the select module. But of course, as you use all 3, you do see improvements even further. I'm going to skip this slide because there are more interesting analyses and conclusions. Okay, so some other things to analyze are that self-discovery does improve a lot of the reasoning structure, but it doesn't guarantee higher accuracy. There isn't anything at each step where it creates this reasoning structure that it guarantees that what it writes into that template is going to be correct. So you still do have inaccuracies. That is something that still would have to be solved, and just solved in general as far as any type of prompting technique. And so you can provide a reasoning structure which provides something that is completely incorrect, such as for this, how many numbers between 1 and 2005 are integer multiples of 3 or 4, but not 12? And it provides a reasoning step that is not correct to the problem at hand. It also can do computational errors. Again, this technique does not test for computation or for accuracy. So when you do build out the reasoning structure, you can introduce the same type of mathematical errors that you have from direct prompting. And so that is still an open problem that needs to be solved. Model versus human, as far as writing these types of reasoning structures, you do have, the point is that you do have that the reasoning structures that the LLM produces, when they compared it with some humans writing very similar types of JSONs, to be very similar to the human readable JSON. So it's very highly human interpretable at the end of the day, while it's also very highly machine interpretable. So that bridges some of the gap in terms of helping us give a better philosophical understanding of what the language representation of these models are. And I guess I included this just to kind of summarize what the results of the paper are. Basically, it introduces a new type of a prompting technique. It creates these very specific templates that improves on chain of thought and improves a lot of the accuracy in the data in very complex data sets, such as BBH, T4D, and math, including and especially for very powerful language models, such as GPT-4. All right, I'm gonna end over here and I'll stop recording so that we have an open floor for questions.